EDX Core Pure, complex numbers 3, modulus, argument and loci, argument definitions for loci. So here we have a single argument definition of a loci. The argument of z minus z1 equals theta. So z1 is a given fixed point shown on the diagram by x1, y1. Z is a loci point shown on the diagram by xy, and we need the argument of z minus z1 to be exactly the given fixed angle theta. So the first thing we need to think about is z minus z1. Z minus z1 is a complex number shown with an arrow there going from z1 towards z, and we need its argument or direction to be exactly theta. So argument is just a mathematical way of defining the direction of the complex number, and it's measured from the horizontal positive real direction, and we need that to be theta. So if I just complete this triangle, just for reference, you can see this vertical side is y minus y1 and this horizontal side is x minus x1. So if we now think about this argument again, the argument of z minus z1 equals theta. Argument means the direction of this complex number shown on the diagram, and its direction can be found by doing tan minus 1 the y direction divided by the x direction, and we need that definition of the argument to be angle theta. So you can see the method shown clearly on the diagram, and we can see the formula we're going to use to find theta. But theta is unique, therefore this argument must be unique. And for the argument to be unique, the locus is a half line from the fixed point z1. You cannot put the other end of the line. If you put the other end of the line in, that would have a different argument. So the only line that has a loci that fits the argument theta is the half line. Interesting little detail, the point itself, z1, is not part of the solution, so you can show that as an empty circle if you just want that little bit more information. So have a look at this example. What does the loci look like if the argument of z plus 2 plus 3i equals pi by 6? The first thing we've got to do is to rewrite the problem just as we did with the modulus loci. So you've got to have it as z minus. So it'll be minus 2 minus 3i. So argument is just direction. So we need to think of this as the direction of z from the fixed point minus 2 minus 3. We need that direction to be pi by 6. So we've got a fixed point shown on the diagram, minus 2 minus 3, again shown with the empty circle. The point itself is not part of the answer, and we need to go off in the direction of pi by 6. So the loci is a half line from minus 2 minus 3 at an angle of pi by 6 from the horizontal. So get it in the right form, and then make sure you go off in that unique direction. We can see the angle here. There's my unique angle of pi by 6 there. Another example just to clarify the method. So here, although we've got the z and the minus sign, it's not clear what Z1 is, so we need to pull out the minus and have a good look at Z1, which will be 3 minus 2i. So make sure Z1 is bracketed and clear. So this time our fixed point is given by the complex number 3 minus 2i. So the fixed point is 3 comma minus 2, which you can see on the direction on the diagram, and the direction we need this time is 2 pi by 3, or 120 degrees. So we've got our fixed point 3 minus 2, and we need to go off at 120 degrees to here. So the direction, and this is only an approximation, is going to be roughly there. There's my 2 pi by 3, which I know is is 120 degrees. So my solution is this half line. It does keep going. The arrow is there to show that it does keep going, and it doesn't include the point 3 minus 2. For further thinking, there's an interesting look at a more difficult case where the argument of z minus z1 over z minus z2 equals theta. There's a GeoGebra file there that you can have a look at, but it is slightly beyond the scope of the syllabus, but nevertheless quite an interesting file to have a look at. In the final session, we're going to be looking at regions defined in the complex plane.